On October 2, 2025, the HiRISE camera aboard Mars Reconnaissance Orbiter captured images of 3I-Atlas at a resolution of 30 kilometers per pixel. That's the sharpest possible view of an interstellar object's nucleus. Sharper than anything Hubble can produce from Earth's orbit, sharper than anything we had for Oumuamua or Borisov. Those images were held for 47 days. The official reason is a US government shutdown. We'll accept that explanation. But let's first look at everything else. To understand why the timing matters, you need to understand the scale of what was watching. By July 2, 2025, the day the Minor Planet Center formally designated this object as 3I, there were already 122 observations logged from 31 separate observatories. That number came together in hours. The object was confirmed active within the same day by David Jewett and Jane Liu, using the Nordic Optical Telescope. Within weeks, the full weight of operational space infrastructure had turned toward it. Hubble, the James Webb Space Telescope, Parker Solar Probe, JUICE, MRO, Perseverance, Spherix, TESS, the ExoMars Trace Gas Orbiter. The complete list runs past 25 instruments. We have never deployed this kind of coordinated attention on any previous interstellar visitor. 3I-Atlas entered the solar system at 58 kilometers per second, roughly twice the entry speed of Oumuamua and Borisov. The observation campaign matched that urgency. Every one of those instruments saw something. They did not all say what they saw at the same time. Here's the map of when the data came out. ESS's Trace Gas Orbiter shot 3I-Atlas between October 3, 2025 and October 7, 2025. Published October 7, 2025. 4 days. China's Tianwen-1, also near Mars during the flyby window, released its HiRIC imagery shortly after. Perseverance was different. Its raw image data is always publicly available, but NASA did not formally identify 3I-Atlas in those frames. An astrophotographer named Simeon Schmaus found it first, working independently, before any official announcement. Parker Solar Probe's WHISPER instrument imaged the object continuously, from October 18, 2025 through November 5, 2025, roughly 10 frames per day, approximately 180 images total. Those were released in December 2025, unprocessed. The fully calibrated, scientifically usable versions have not been published. And then there's JUICE, 5 instruments, more than 120 images, taken across November 2, 2025 to November 25, 2025. The data arrived on Earth on February 18, 2026 through February 20, 2026, 3.5 months after the observation. The first image from Janus was published on February 26, 2026. Each of these has an explanation. Let's take them seriously. The HiRISE gap is the most documented. The US federal government shutdown began in late September 2025 and effectively froze NASA's public communications infrastructure. The imaging itself, the decision to point MRO at 3I-Atlas, had been planned well in advance. HiRISE principal investigator Shane Byrne at the University of Arizona and MRO project scientist Leslie Tampari at JPL were both publicly connected to those images before they came out, and both presented the data at a NASA press conference on November 19, 2025. That's the date the 47-day gap ends. During that same window, that same October, ESS-TGO was 4 days from shot to publication. Tianwen-1 was similarly prompt. 3 agencies, 1 object, very different clocks. The shutdown explains HiRISE. What explains Parker Solar Probe? WHISPER, the Wide Field Imager for Solar Probe, is not a conventional telescope. It's designed to image the solar corona and solar wind structures, not comets. When it captures something like 3I-Atlas, the raw frames carry artifacts from the instrument's primary calibration baseline, which is tuned for diffuse, low-contrast plasma features, not a bright transient nucleus surrounded by a coma. Releasing raw data quickly is a feature of NASA's culture for submissions. Getting to scientifically rigorous final products takes longer. That's not a policy. It's physics and pipeline engineering. All of that is almost certainly true. It also means that the approximately 180 images taken at close range during 3I-Atlas's perihelion passage, while it was at its most active, closest to the Sun, losing mass at its highest rate, are still not in final form 4 months later. The raw versions exist publicly, but calibrated analysis hasn't come from the science team yet. There's also the Psyche spacecraft. On September 4, 2025, Psyche passed within 45.2 million kilometers of 3I-Atlas, closer than most observatories had access to. The distance is confirmed in the literature, specifically in a preprint cataloged as ARXIV:2508.15768. What Psyche's instruments captured is not confirmed. The cited reason is potential interference from the spacecraft's ion propulsion system during thrust operations. That explanation is technically plausible. It also means we don't know what Psyche saw. 2 instruments, 2 gaps, 2 separate technical explanations. And then one more that stands apart. JUICE. The Jupiter Icy Moons Explorer was carrying 5 scientific instruments when it passed within 64 million kilometers of 3I-Atlas on 11/04 and November 5, 2025. JANUS, the imaging system. Almagis, a spectrometer covering the visible and infrared. SWI for submillimeter wavelength. PEP for particle and plasma environment. UVS in the ultraviolet. The observation campaign ran continuously from 11/02 through the 25th. JUICE then went quiet. Not because of a shutdown or a thruster issue, but because its high-gain antenna had been used as a thermal shield during the solar flyby. Transmitting large data volumes through a degraded link takes time. That time was 3.5 months. The data arrived at ESA ground stations on 02/18 to February 20, 2026. The first released image, a single frame from JANUS, came out on February 26, 2026. The science team has announced that the first combined results, from all 5 instruments, will be released in late March 2026. The spacecraft that passed closest to 3I-Atlas during the observing window was the last to speak. Does that seem unusual? There's a mundane explanation for every piece of this. And the pattern still accumulates. Which brings us to now, March 16, 2026. 3 days from this recording, 3I-Atlas makes its closest approach to Jupiter, passing within 0.358 AU, roughly 53.6 million kilometers. The positional uncertainty on its orbit right now, after more than 8 months of observation by dozens of instruments, is still plus or minus 600 kilometers. The Juno spacecraft, which is already at Jupiter, will not be redirected for a closer look. It's running on minimal fuel reserves with degraded propulsion. There is no other dedicated asset in the Jovian system, close enough to do what JUICE did in November. The JUICE data exists. It hasn't been interpreted publicly yet. The object is now at Jupiter. The window for close-range observation from anything in the inner solar system is closed. There are 3 additional facts that don't fit neatly into the timeline story. They belong in a different category. Not delays, but the data itself. On November 5, 2025, an observer in Spain recorded 3I-Atlas after perihelion and noted the absence of a dust tail. This is unusual for an object that had been actively outgassing, at rates suggesting it had lost more than 13% of its total mass during perihelion passage. Where that material went, why no tail formed, that remains without a published explanation. On December 27, 2025, Hubble imaging processed by T. Scarmato and Avi Loeb revealed 3 jets emanating from the nucleus, symmetrically distributed around it, at near-equal angular intervals. Random subsurface ice pockets can produce jets, but symmetric, evenly distributed ones are statistically less common. No published analysis has addressed the geometry directly. And then there's the orbital plane. 3I-Atlas is moving in retrograde, effectively backward relative to the solar system's rotation, on an inclination of about 5 degrees from the ecliptic. The probability of a random interstellar trajectory arriving at that particular orbital alignment, that close to the ecliptic plane, is approximately 0.2%. None of these 3 facts require an extraordinary explanation. Standard cometary physics can potentially account for all of them. None of them currently have one on record. In the last week of March 2026, ESA will release the combined scientific results from JUICE's 5 instruments. MAGIS carries spectroscopic data on the coma composition at multiple wavelengths, the same coma where spherics already detected carbon dioxide, carbon monoxide, water, organic compounds, and rocky material in December 2025. PEP will have measured the plasma environment around the object at close range. UVS will have sampled the ultraviolet signature. This is the most complete close-range dataset ever collected on an interstellar object, and it's coming out in the same days that 3I-Atlas passes Jupiter for the last time. We have a documented pattern of delays, 3 physical anomalies without published explanations, and data from the nearest observing spacecraft, arriving exactly at the moment the object moves beyond reach. What do you think will be in the JUICE results when they come out? And will you know what to look for?